All right, William, can you guys hear me okay?
Yeah, we can hear you.
Awesome. All right, so let's get started. Couple quick announcements. So first, I want to thank you for continuing to wear your masks to help protect your fellow students. I know there's a lot of stuff going on around right now. A lot of students are sick. So, wearing the masks and staying home when you're sick is super helpful for preventing the spread of all sorts of things. And welcome to anyone who is watching the live stream, who's at home not feeling well. I hope you feel better soon. So just a reminder that we do have a special workshop this week on graphing transformations. So William has another workshop on Thursday where he will be looking at the transformations of graphs. So that's things like moving graphs up and down, left and right. And he's going to demo Desmos, which is an online tool you can use to get pictures so you can do some quick thinking about graphing properties and things like that. So that's coming up on Thursday. And the link to that I emailed to you guys. You're a little frozen. I hope I'm still coming through. So the projector has been replaced. So hopefully that's working well now. The internet is a little more stable. They've hardwired an Ethernet connection, but they've also told me to inform you that if you could try to refrain from going on the internet while you're in Marcus, that'll help preserve the stability of the connection. So, if you have a laptop, but you're not taking notes, if you could put it away. If you are taking notes, that's fine, but try not to go on the internet. That'll help make sure that we don't get too frozen along the way. So those are the big ones. We have our next quiz due tomorrow night, and then homework and quiz due on Sunday. So again, I would encourage you to start the homework early, drop in help today from 2 to 9, get some of that done before the quiz tomorrow so that you're in good shape for that. So today we're supposed to cover a summary of 3 topics, which is exponential functions, logarithmic functions, and economic applications. I am going to switch the order a little bit just for the sake of time. I don't think we're going to get to all 3, but I want to make sure that we do exponential functions well, because that's a sort of algebra thing that students struggle with a lot. So we're going to start with exponential functions, Then we'll go back to our economics, our cost and revenue. And if we have time, we'll do the natural log, but that one is very brief. So if we don't get to that, I'll just send you a review video. But if you're comfortable with that, then you should be all set anyway. So we're going to start with exponential functions. So I'm going to go ahead and switch to the DocCam so we can get started on those notes. All right. So exponential functions are a specific type of functions, but to really have the context of what we're doing with exponential functions, I just want to remind you about the other type of function that we look at that often gets confused, and that's a polynomial. So a polynomial function, that's like your x squared, your x to the fourth, your x cubes. The hallmark property of the polynomial is that the variable is in the base. And we love polynomials. Polynomials are easy to work with. Often when we start something completely new, we look at a polynomial first because the behavior is predictable and the algebra is not usually too crazy. But we also have other types of functions, and the function type that we're going to look at today are exponential functions. And so we'll compare this in a second, but an exponential function is a function of the form y equals k times a to the x. And what I want you to notice here is where the x is. So here, the variable is in the power. So that is the key difference between a polynomial and an exponential function, is where the variable is. If it's in the base, polynomial. If it's in the power, now we're talking about exponential functions. So we're going to look at exponential functions, how to deal with them, what sorts of things they tell us, and just sort of in the back of your mind, keep in mind, one of the key things we want to be able to do is just recognize that we have an exponential function. So look at a function and know if it's a polynomial or an exponential function. So this is the most generic form. And one of the things that is also important here are that a and k are constants. So these are numbers. These are not variables. The only variable here is x. So quick example, 3 to the x, that's an exponential function. The variable's up in the power. 10 times 5 to the t, exponential function, because the variable's up in the power. Now, one thing that students will sometimes try to do that gets them into trouble. So you cannot combine the 10 and the 5 in any way to simplify. So we cannot make this 50 to the t or anything like that. The 5 to the t is a function in itself. And so the 10 just has to multiply it. We can't combine those in any way, shape, or form. Okay. So that's sort of the very general exponential structure. The key hallmark being that the variable is in the power. So the first thing we want to do is we just want to make sure that we can plug things into exponential functions to some degree. So we're going to start with just an exercise here where there's 4 different exponential functions. So 2 times 3 to the t, 0.5 times 1.2 to the t, right? So on and so forth. And what I want you to do is to take out your calculator, or if you have a laptop that you tend to use a calculator on or whatever, I just want you to plug in 3 into each of these 4 functions to get the numeric output. This is mostly to practice where the parentheses go and to make sure we're able to plug things into exponential functions. So I'm going to give you 2 minutes to go ahead and try to plug in 3 into each of these. The TAs will sort of walk around, and if you need help figuring out where to plug things in on your calculator, you can ask one of them. But hopefully this is something you've done before. So try that out, take a quick 2 minutes and see if you can do those 4 plugins. Okay, so take about 30 more seconds just to finish plugging in a 3 everywhere. All right, so I've written down what I got when I plugged in these numbers, and hopefully you are getting the same thing. If you are not, then it might be a matter of where your parentheses are or how your calculator is set up. But I do want to take a minute to talk a little bit more explicitly about part D. So part D, we have y equals 2e to the t. So this e is a number, right? So it's like pi, where it's a mathematical constant that has a value. The value is approximately 2.71. So when we are plugging things in and we have this e, there's still a number in the base and the variable is still in the power. So I want to show you for part D just how I plug this into my calculator, because this is sometimes something that students end up plugging in the wrong way. And so I just want to make sure we're all on the same page about the e's. So here, when I'm looking for my function, I have the 2 first. So I have 2 times. Now I need e to the 3, right? Because I'm plugging in a t equals 3. My e is hidden behind this natural log. It says ln, it's right next to the 4 button, but behind it in blue, it says e to the x. So I need to hit second and then hit the ln button, and it puts the e in there. That's where the e is. It's not the button that says exp, which is in different places. But now I can plug in the value that I want here, which was 3. So I have 2 times e to the 3. I can see that this looks exactly like this structure, that I didn't do anything too crazy. And then I hit enter. Oh, the backlight's really strong, which gives me 40.171. So when you're dealing with that e function, that's where it's tucked away. It's behind the natural log if you have a TI calculator. If you have a Casio or another type of graphing calculator, it's probably somewhere near the natural log button. And if you're working in like a browser on like Wolfram Alpha or something, you can put in an E on your keyboard to represent that number E, okay? So that's plugging in those values. That's sort of the first step of getting comfortable with exponential functions. Now, the reason that we really end up using exponential functions so much in calculus is because a lot of things that happen in biology and chemistry and in the natural sciences happen to have an exponential form, right? So they are modeled in a way that exponential functions come up naturally. So we have a general form for when we're talking about growth and decay, which is the most common way that we will see exponential functions applied to the life sciences.
Oh, Adina.
Yes.
Oh, we
Yep.
lost you for 1 second. Can you repeat that last sentence?
Yes. So the general form is necessary because we do find that we have a lot of growth and decay applied to the life sciences. So the general form looks like this. So we have P naught A to the T, or P naught times 1 plus R to the T. Now, I want to point out, this is the same exact thing as the general form. We're just calling K P naught, and we're saying that A is equal to 1 plus R. Now, what does that mean? When you hear the word naught, like P naught, R naught, Q naught, that means it has a subscript of 0, right? So when we use subscripts in math, we're just indexing something. So we'll say something like P sub 1, which is P with a subscript of 1, P sub 2. But for 0, we call it P naught. It sounds really goofy, but that's just the way we say it. What that means in this context, when you have this naught, is that it's an initial amount, right? So at time equals 0, we have an initial amount of whatever it is that we are modeling. Because if we were to plug in a 0 here, we would have a to the 0, which is 1, times this amount. So we just get this amount back. So we look for context clues within word problems about the initial amount is, and that gives us this P naught, okay? T is our variable. It's almost exclusively time when we are talking about growth and decay and using this form. Up in this other version, it doesn't have to be time, it can be anything. But when we're talking about growth and decay, we are looking at what happens over time. Now, this A and the 1 plus R. So 1 plus R is how we determine our A. And so there's some information about what that means. R is your growth rate, okay? And your growth rate is how much your function is changing in a decimal representation of a percentage. So if your population is growing by 20%, your R is 0.20. If your population is growing by 45%, your R is 0.45. It's the rate at which you are growing. Now, if your function or whatever you're modeling is decaying, then your R will be negative. So if you're decaying by 15% per year, your R is negative 0.15. So R is positive if you're growing and negative if you are decaying, okay? So that means that our A, okay, is either going to be greater than 1, which means you have growth, right? Your R is positive, you've added something to 1 to make it bigger than 1, or your A is between 0 and 1. Okay, so if you are between 0 and 1, your R was negative, and we are modeling decay. Okay, now, one important factor to point out here is the difference between a percent change and a constant rate of change. So we started talking a few classes ago just about linear functions. We just said y equals mx plus b. Well, the slope is a constant rate of change. When you have a linear function, the slope tells you how much you change every time you increase by 1 unit. It always changes the same amount in the dependent unit. That's the m in y equals mx plus b. When you have exponential functions, however, your change is a percentage rate of change. So instead of always increasing by 5 units, you're increasing by 5% each time. So it's not the same number each time, but it is the same percentage. Okay? So we want to take all of these important factors because all of these are important, right? When we have growth, when we have decay, what is R, what is the initial population, and we just want to sort of get used to playing with these different factors. So I'm going to have you try out this problem where we have 4 different populations, 1, 2, 3, and 4. And these populations are in thousands. So what that means is if you plug something in and you get a number out, it's in thousands, right? So if you get out a 5, it's really 5,000. And our time here is in years since 2010. So the population units are in thousands, time is in years since 2010. I want you to try to answer these 4 questions based on these 4 populations. So the first question, which town has the largest percentage growth rate? The percentage growth rate, we're looking for R. Part B, which town has the largest initial population? So we're comparing P naughts. Part C, which town has the largest population in 2015? So you'll have to find the population for each model in 2015 to see which one's the biggest. And then part D, which towns are growing and which ones are decaying? So we'll be looking at that A value, which is in the parentheses, to figure out if it's growth or decay. So I'm going to give you 3 minutes to try this out. See if you can answer these questions. Feel free to check in with someone next to you. Any TAs that are there will walk around and then we'll go over it together. Okay, so you have 3 minutes. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so let's take a stab at these 4 questions and see if we can work through and figure out what our answers are here. So for part A, we're comparing the growth rates, which means that we need to figure out what R is for each of our populations. So for our first population, we have 1.37. Now remember, that's our A, but our A is 1 plus R. So whenever we have a positive growth rate, it's a little bit easier because if it's just 1 point something, then that decimal is our R. Our R. Can't say that. Okay. So our growth rate here is 0.37 or 37%. Typically in this type of question, we're just reporting it as a decimal, but it really depends on how the question is asked. So let's skip to number 4 real quick and do the same thing. This one's a little bit easier. So for number 4, our R, this is positive 1.28. So our R is 0.28 or 28%. So again, if it's greater than 1, it's just that decimal that's after that. If, however, you have a situation in which you are less than 1, like we do here, what we need to do is we need to take that factor, that 0.68, and I'll come over here and set it equal to 1 plus R, because we need to subtract 1 from both sides, right? So when we do that, we get that R equals negative 0.32. So again, if your number is less than 1 in the base, we had some sort of decay and your R is going to be negative. Similarly, if we take 0.35, set it equal to 1 plus R, so we're subtracting 1, we get R equals negative 0.65. So now that we have all our R's figured out, we want to figure out which one is the largest. Now, this word largest can be really confusing depending on the context. So I want to be really clear about how we compare numbers in this class, which may be different depending on if you're in physics or in math. But when we talk about the largest value, I want you to think about a number line. So if we were to put these all on a number line, which one would be the furthest to the right? that one is going to be the largest, right? So like if 0 is here, 2 of the R's are over here and 2 of them are over to the right. So positive numbers are larger than negative numbers, which is a little bit tricky because it really depends on how you're dealing with magnitude. But for this class, we're really looking at on a number line, which would be the farthest to the right, which will be our 0.37, right? Because 0.37 is bigger than 0.28 and positive numbers are bigger than negative numbers. So here, my largest growth rate is going to be function number 1 with R equals 0.37. For part B, we are considering initial populations. So initial populations are represented by these numbers in front of the entire function here. So that's our P naught. We have 250, 1200, 125, and 500. Those are the 4 initial populations. And using the same method as part A, if we were to put those on a number line and ask which one is the biggest, the 1200 is going to be our largest population. So function 2, 1200. Okay, so for comparing initial values, you're always looking at these numbers that are in front of the exponential function. So for part C, we want to know which town has the largest population in 2015. Now, what I want to point out here is that in 2015 can be translated to say T equals 5. Because remember, T is in years since 2010. So if we're talking about 2015, we are evaluating what's happening at time equals 5 years since 2010. So we need to plug a 5 into every single one of these functions so we can compare the population. So when I plug it into the first function, I get 1207. When I plug it into my second function, I got 174. You're always welcome to check my math. Sometimes I make small arithmetic mistakes. For the third one, I got 0.656. And for the fourth one, I got 17.99. Okay. Now, because this question is just asking me which one is the largest, I can compare these numbers to see which one is the biggest, right? Which one's the furthest right on a number line, which is population number 4, right? 17.99. However, I want to point out that if I had asked you what is the population of town number 2 in 2015, and you plugged in a 5.
You got me.
What's that?
Oh, sorry, we lost you for about 10 seconds.
Okay, so in comparison, we can answer this question, right? We can look at these numbers and say 1717 is the biggest. So the answer is 4. But if the question had been, what is the population of town 2 in 2015? I got 174. I have to remember that that's in thousands, right? So if this is Wiley, I would either need to have something like 174 and then the word 1,000, or I would need to write out 174,000. So this units becomes really important if you need to actually state the population. For comparison, we don't need to multiply everything by 1,000 because the biggest one will remain the biggest one, but it's important to remember that for different types of questions. For part D, which towns are growing and which are decaying? So our growing towns are the towns that have an A bigger than 1. So that's number 1 and number 4. Which towns are decreasing? Well, those are the ones that have an A less than 1, which are towns 2 and 3. So again, we can take a look at the base of our exponential function and just figure out if it's growing or decaying by comparing it to the number 1. Bigger than 1, we're growing. Smaller than 1, we are decaying. So that's sort of our basic plug and chug type exponential functions, which hopefully is all coming back to you because I'm sure you've all seen exponential functions at some point, although it may have been a while. But now I want to talk about the harder thing that we do with exponential functions. This doesn't mean it's hard. It's just harder than plugging in, and it just takes a little practice. And once we get used to it, it's pretty good. And that is creating models of functions. And this is not difficult because it's an exponential function. It's just getting used to creating models takes a little practice. So we have 3 scenarios here where we are trying to create models. And when I say create models, what I mean is find a function in the form that you are looking for, which here is primarily the form p equals p naught a to the t, although this sub question is an exception. Okay, so what we're going to do is I'm going to have you try a couple of these. There's 3 different types, and I'm going to let you pick the type that you feel most comfortable with. So for the first one, we have some adrenaline in the body, and it starts with 15 milligrams. And we want to come up with a model of how much adrenaline is in the body if, part A, we are increasing by 0.4 milligrams per minute. Part B, we are decreasing by 3% per minute. I want to point out this is a percentage. This is a constant rate of change. Those are going to be different types of functions. The second one is a graph. How do we come up with something in this form if we have a picture? The only thing you really need from this are these points. So I'm just going to write them a little bit bigger. Okay, we have 2 points on this graph. We can see that it's curved. So we want to find an exponential model to fit that data. And then the third problem, we just have a table, right? And we want to take the data from the table to get this model. So I'm going to give you 5 minutes, which will not be enough time to do all 3. I want you to pick one that you want to start with. Maybe you're interested in the graph or the table or the word problem. Pick whichever one you want to start with. I expect that you'll be able to get through maybe 2 of the 3, but maybe not all 3, and that's okay. Okay, we'll go through them together, but I'm going to give you 5 minutes to work on it. The TAs will come around, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so let's go through these and see how we can set up our exponential models for each of these different types of scenarios. So for the first one, let's think about what the key information we're getting from the problem is. We have an initial amount of 15 milligrams. We're looking for a formula for A, our dependent variable, with an independent variable of T. So the sort of heart of this problem is understanding the difference between the wordings of these two sub-questions. So if we're increasing by a set amount, that means that we have a linear function, okay? So here, for part A, we're not setting up an exponential model, but instead a linear function to represent what's happening. So again, a linear function, y equals mx plus b. Here my variables are a little bit different. So I'm going to have a equals, because a is my dependent variable. My slope is my rate of change, which here is 0.4. My independent variable is t. And then the initial amount is the amount when your independent variable is 0, which is the same thing as the vertical intercept. So that 15 is actually our b. So for part A, the model of this function is going to look like this. It's linear, and I know that because it's a constant rate of change. So that's different for part B, where we have a percent rate of change. So for part B, we're going to have A equals, because again, A was our dependent variable here. And now if we look at our form, we know that we need the initial amount, so P naught, the initial amount we start with, which is 15, times A to the T, okay? So our A here is what we need to figure out. If we're decreasing by 3%, that means that my R is negative 3%, which translates into a decimal of negative 0.03. So if my R is negative, I am subtracting the 0.03 or adding negative 0.03 to 1. So I have 0.97. Okay, and I know that if this number is less than 1, I should be decreasing, which is what's happening here. One thing I want to point out that's going to be really important on Wiley in particular is that when you are asked to put in a model, you have to use the variables that are given to you in the problem. So if you were asked to find a model for part B and it said A equals, and then there was a box, and you put in 15 times 0.97 to the X, you would get it wrong, okay? Because the variable here is T. 90% of the time, the variable is T, but sometimes it's X and sometimes it's Q. So if you are doing a problem where you're setting up a model in Wiley, if you get it wrong, the first thing I want you to do is just make sure that you use the right variable, okay? Okay, so for the sort of word problem types, we just want to get used to the wording and recognizing percentages so that we know how to set up our models. For the second one, we are looking at a graph, and we are trying to figure out how to come up with a model from the graph. So P equals P naught A to the T. As a reminder, our P naught is the initial value or the value when T equals 0. So if we look at our 2 points here, we notice that this first point is the intercept and gives us the value when T equals 0. Okay, that's not a coincidence. That happened by design to help us figure out how to set up this model. So my P naught here is going to be this dependent value of 80. Okay, and again, I know that from this point that's given on the graph. So as a reminder, your variable here is T, which means I need to solve for A, because I want this in my final model to remain a T. So in order to solve for A, I'm going to use the other point. So not the one with 0, 80, because if I plug in a 0, it's going to knock out this whole term. I'm going to plug in the other point to solve for A. Now, what's really important here is that we plug the values into the right place. So here, my independent variable is T. So my 6 needs to go in for T, okay? So when I set up this equation, I have 180 equals 80 A to the 6th. One of the #1 problems that people get wrong when they're doing this type of work is that they plug the 6 into the wrong place. So they have 6 equals 80 A to the 180. So just make sure that you're plugging in the numbers in the right place. So now to solve for A, I'm going to divide both sides by 80. It'll cancel on the right. This is a terminal decimal. So I'm going to turn this into a decimal just to make the visual a little bit easier. You can certainly leave it as a fraction or reduce the fraction. You should only turn things into decimals if they're terminal decimals. So what that means is this is not 2.2516852. It stops after the 5. Okay. If it's not a terminal decimal, like 1/3, you should leave it as a fraction. So now I have to solve for A, and I have this 6th power. So I have 2 options to deal with the 6th power. I can either, my first option, is take the 6th root of both sides.
Hey, Dina, we lost you for a few seconds there, just about 10 seconds.
So once we've reduced our fraction here, and we're down to this line, we need to get rid of this 6. There's 2 ways we can do this. The first is to take the 6th root of both sides. That's something you can do on your calculator. You should have an nth root button on there somewhere, and the 6th root and the 6 will cancel, leaving you just A. Or the more common approach is to raise both sides to 1 over whatever the root you're trying to get rid of is. Okay, so if you raise A to the 6th to the 1/6, these cancel. And so we need to do 2.25 to the 1/6 power. So when you do that in your calculator, that's going to give you A. And you're going to get 1.1447. Okay, so this tells me a few things. 1, that I have growth, right? This is bigger than 1, and that makes sense because my function is increasing, it's growing. My rate here is approximately 14.47%, but I'm not done, right? Because the problem wanted me to find a model, so I have to put it all together. So remember, my initial amount was 80. Now I have my A, 1.1447 to the power of T. So now I'm done. I have to put all the pieces together to get my final model. And it's really helpful to have models for all sorts of predictive analysis, because now if I want to know what the value is at 10, at time equals 5, at time equals 20, I can plug it in to get the value for this particular function. So that's with a graph. And the third way we set up models is from the table. Ooh, my marker's running away. So again, we want something in model form. And again, we start by thinking about P naught. So P naught is the initial amount when T equals 0, right? So our initial population of whatever we're modeling. So here in the table, I can find that data because when T equals 0, my Q, the amount of drug, is 250. I get that directly from the table. So that tells me my initial amount is 250. Okay, so I plug that in. Now, similar to the last problem, if I want to solve for A, I need to plug in another data point. Well, there's a whole bunch of data points in the table. I can plug in any one of them to solve for A, but I'm going to pick carefully to try to make my algebra as easy as possible. So I'm going to use the point 150 because dealing with a T equals 1 is going to make the algebra a little bit easier. But again, you can plug in any one of these points to solve for A. So when I plug in my point, again, I want to make sure I plug in the correct place. I get 150 equals 250 A to the 1. So my 1 got plugged in for T, and my 150 got plugged in for my population later. Okay. I picked it this way. The reason I picked this point is because if you have A to the 1, that's just A. Anything to the 1 power is just itself. So it just makes it a tiny bit easier on the algebra. So to solve for A here, I divide both sides by 250, and I get A equals 0.6. Okay. But again, getting the A is not enough. I have to put the final model together. And I'm going to be a little careful here because my variable in the table is Q, not P. So I don't want to mess anything up. So we're going to say Q equals, because that's my dependent variable, 250, my initial population, times A, 0.6, to the, my independent variable is T. Okay. So my final model for this table is 250 times 0.6 to the T. The nice thing about tables is if you want to check to make sure you did it right, you can plug in any one of the other points to make sure that the dependent value matches the independent value. It's a good way to check your work. Okay. So these are 3 ways that we set up models for exponential functions. It's something we do pretty often. And it's something that feels intimidating at first, but once you've practiced it a few times, you realize it's not that bad, that they're all pretty similar. So hopefully having some examples of each type will help you as we do these more in the class. Okay, so we're gonna shift gears now, and we're gonna go back to our application of economics 1.4. And so I will mention that, you know, these 3 sections, 1.4, 1.5, 1.6, are supposed to be review, but in my opinion, 1.4, which is application of economics, is not really a review because not everyone studies economics before they come to math. So it's important to me that if you've never seen economics, that we're really clear about what we're talking about, because it comes up a lot. We do a lot of business applications in this course. So we want to make sure we know all the terminology and we know what's going on. I'm fairly confident you have all seen exponential functions in your life at some point, whether you remember or not. But I know that a good chunk of you have never worked with economics before. I will also say that if you're taking like Econ 103 or Econ 104, you may see some of this stuff come up during your semester in that class as well. And so you'll be talking about the same types of things that we are looking at right now. Okay, so we will be doing some terminology today. we'll do some of the application stuff, but a lot of it is just making sure that we're on the same page about definitions so that later on when we're talking about them, we all understand, I guess here, the mindset of business. So we're going to start by talking about cost, okay? And this is a little tricky because when you think of the word cost, or at least when I think of the word cost, I'm like, how much does this watermelon cost, right? So I associate it with price. But that is not what we're doing here. When we're talking about the price of something, we will actually use price. So when we talk about cost, we are talking about it from a manufacturing standpoint. And what that means is how much does it cost me to make some sort of good that I'm going to sell later? Okay. So for example, if I was going to sell UMass sweatshirts at the bookstore, right? I'm trying to figure out what my costs are going to be to make those sweatshirts. So it's going to be things like the cost of the material, the cost of the thread for sewing, the cost of the inking to put the print on the front, the cost of the little shoelace that goes through the hood, right? So I'm thinking about the cost to make the product. Okay, so whenever we're talking about cost in this class, we're talking about it from a manufacturing standpoint. So how much does it cost me to make something or to produce something? Okay, for now, we are assuming that cost functions are linear. Okay, we will explicitly talk about how to change our thinking for nonlinear functions in chapter 2. But for right now, the way we start off our studying of this, we are just saying cost functions are linear, okay? And so with linear functions, we have something of the form y equals mx plus b, but in a new context. So cost functions, we are going to write as C of Q, C for cost, Q for quantity. So when we do business applications, our independent variable is always going to be Q for quantity because we're talking about how many we make, right? So the cost function has two really important parts, which have to do with the slope and the intercept. So the first part is called variable cost, okay? So variable cost is the slope, and the variable cost is going to tell me how much additional cost I will incur if I make one more sweatshirt or whatever I'm producing. So this type of cost really often goes with materials, right? So for every additional sweatshirt I produce, I have to use some more of my material, my sweatshirt material, some more of my thread, some more of my printing ink every single time I make a sweatshirt. So what is that cost every time I make one more of them? The other part is our B, and that's called fixed costs. Okay, so fixed cost is sort of the upfront one-time investment that you pay that does not depend on how many you produce. So for example, in my sweatshirt example, if I were to buy a sewing machine, that would be a fixed cost because I'd only buy it once. I wouldn't have a different sewing machine every single time I made a sweatshirt. It's a one-time deal. And the key thing about fixed cost is we can determine fixed cost by looking at the cost when quantity equals 0. So how much money did I spend before I even made a single sweatshirt? Right? So maybe I bought a sewing machine, maybe I bought a factory, I don't know, right? So the things that you would just sort of buy one time and don't depend on the number of sweatshirts you make, okay? So then our general form for a cost equation is M times Q plus B, right? So it's almost like MX plus B, but we're using Q instead. And the other sort of strangely specific caveat that I want to bring up here is that variable cost is also called marginal cost. And the difference between these two words is that variable cost is specific to linear functions. Marginal cost can be applied to any type of function. For our context right now, marginal cost and variable cost mean the same exact thing because we're only talking about linear functions. Later on, when we move away from linear functions, we will bring the term marginal cost with us and leave variable cost behind because variable is specific to linear functions. So what you need to know right now is that they mean the same thing until we say otherwise. Okay, so we have this sense of cost and we know that they're linear. So the first thing we want to do is just get a sense of what that means in terms of cost functions and to bring up some sort of domain restrictions for cost. So there's going to be two quick scenarios and we're going to talk about what this looks like graphically and what it means in context. So let's consider a situation where fixed costs are small, but marginal cost is high. So remember, fixed cost is your plus B. Marginal cost is your slope. So fixed costs are small means that our vertical intercept should be down near 0. So we should be crossing through somewhere near the bottom of this axis. Marginal cost is high means that the slope is steep, right? The bigger that m gets, the steeper the function. So there's not one right answer here, right? There's plenty of functions that satisfy this, but let's just draw a couple in, right? Fixed costs are low, so we cross low. That slope is pretty steep, right? We could have an even lower fixed cost, an even steeper slope. Also an example of low fixed costs and high steep slope. Here's another one, okay? So having this idea about marginal cost, creating the slope to be really steep, is going to be important when we look at things, you know, in context later on. And so one of the things I want to point out here is that for our cost functions, they're always going to be positive. So the cost is a total cost where we are adding up our total costs and presenting it as a positive number. So, you know, my cost might be $20,000 to produce 100 sweatshirts, right? But I present it in a positive fashion. So costs will be positive and the slopes will also be positive, okay? Because slopes are variable cost. So it doesn't make sense for a slope to be negative in this context. It has to be positive because we are adding on a cost every time we make another product, okay? So cost will always be positive, the slope will always be positive. Let's look at another example of this type, where now there are no fixed costs, but marginal cost is small. So no fixed costs. That means that B equals 0. Marginal cost is small. So my function is not steep, right? Because the marginal cost is the slope. So all of my possible functions need to go through 0, 0 because my B has to be 0. However, there's a lot that satisfy this and are not steep, right? Something like that, that's pretty flat. So that has a marginal cost that is low. It could go even lower, right? So a very, very small marginal cost. Something in between. Right, so these are all linear functions that have no fixed cost and a small marginal cost. The slope is steep. So these pictures are really meant to help you understand how marginal cost is directly, it is the slope. So we're talking about slope, but in this very specific context. Okay, so let's look at a practice problem here. So suppose a company is producing ceramic pineapples. The cost to purchase the pineapple mold and the kiln is $20,000. A kiln is like a really hot oven that you put ceramics in. So these are incurred even if no pineapples are made. The cost of labor and raw materials are variable costs, and since these depend on how many pineapples are made, the variable costs are $6 per pineapple. Assuming that cost is linear, I want you to find an equation, a cost equation to model this, and then I just want you to describe what that variable or marginal cost means in this context, okay? So take 2 minutes. I want you to jot down what you think the function is, and then just jot down what you think that variable cost or marginal cost means. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so if we want to set up our model here, we really just need to figure out which number is our variable cost and which one is our fixed cost. So here my variable cost is $6. So I have 6 times Q plus 20,000. Okay, so this is my cost function. Even if I make 0 pineapples, I've spent $20,000 on the molds and the kiln. And then it's going to cost me another $6 in materials, which is probably clay and paint here, for every pineapple that I actually make. So part B says determine the marginal cost and explain what it means in this context. So again, right now, marginal cost is the same as variable cost. So here, my marginal cost is $6. And what that means is for every additional pineapple that I make, I'm gonna get another $6 added to my total cost. It costs me another $6 every time I make a pineapple, okay? So that is cost. That is one piece of sort of a big picture. The next piece, okay, is called revenue. This is also from the producer standpoint. So in all these scenarios, we are talking about making, selling, and doing things from the producer standpoint. So cost, kind of a bummer, right? We're putting out all this money. We want to make money. So the sort of balancing side of cost is revenue. And so revenue is going to tell us how much money that we are going to take in from selling our items. So this is where price comes into play. So revenue, we use R for revenue. Our independent variable is Q, but the general function is P times Q, where P is the price. And when I say price, I'm talking about the price that we are selling an item for. So if, for example, I sell my sweatshirts for $100 each, my revenue function is 100Q. If I sell them for $200 each, my revenue function is 200Q. So whatever price I set, that's a constant, that's part of the revenue function. And then
Okay.
Q is my variable to
Adina,
determine how many I plug in. Yes.
we actually lost you at that last sentence.
Okay, so revenue is going to be price times quantity, where that price is what I'm setting to sell my item at. So let's look at an example here of how I'd set this up. So I've decided to open a store that sells gourmet cookies for $9.99 per tin. In this scenario, my good is being sold, so this $9.99 is a price. My revenue function here is going to be $9.99 times Q. So if I sell 1 tin, my revenue is $9.99. If I sell 2 tins, now I'm at $18.98 or whatever it is times 2. Okay. In this scenario, I want to know how much revenue I have if I sell 221 tins of cookies. So my revenue will be $9.99 times 221 tins. If I multiply those together, page that has my notes. We are going to get 2207.79. And so here is a good place to bring up the fact that when we talk about cost and revenue, we're talking about money, right? How much money did we spend? How much money did we bring in? So when we talk about money, we're talking about the US dollar for our context. And so the way our money system works, we'll be rounding to 2 decimal places because our currency system has 2 decimal places for change. If you were doing this kind of work in another country, you would need to look at what their currency looks like for the units. But here we're talking about dollars. Okay. So let's look at another example that's going to give us a picture of revenue so we can talk about the constraints of revenue as well. So suppose that ceramic pineapples are sold for $20 each. Okay, so here that's a price that we are selling things for. Find a formula to represent the revenue function and sketch it below. So here I have 20Q. Now notice with revenue, it is a linear function, but there is no B. And why is that? Because you're not going to make any money if you don't sell anything. So there's no revenue unless you are selling things. So B is always 0 with revenue. So my function is 20Q. I'm going to go here. Let's see, 5 times 20 is 100. So my revenue function, if I were to graph it, is going to be linear. It's going to look like this. It's going to keep going on up this way. Okay. But what I want to point out, yeah.
We lost you when you were explaining why there was no constant.
Oh, so there's no plus B because you don't make any revenue if you don't sell anything. So B is always 0 in this linear term. So in order to make money, we have to sell some pineapples. Here, revenue is also always going to be positive, just like cost, we report it positively. And because our price is also always going to be positive, it doesn't make sense to sell something for negative money. We always have an increasing linear function for revenue. The more expensive the item is, the steeper the slope. Okay, so that's our revenue, price times quantity. And so now we need to put that together with cost, right? So it's great to take in all this money in terms of revenue. We don't want to be spending a whole lot in terms of cost, but how do we put them together? So the piece of the puzzle that we need here is called profit. So profit, as you can imagine, is the amount of money we take in from selling our item minus the amount of money we spent to make the item. So profit, you would really want it to be called P, but we use P for population. So instead, we're going to use pi, the Greek symbol, often associated with P. And profit is revenue minus cost. So the amount of money that you take in minus the amount of money that you spent. Okay, that gives you your total profit of your manufacturing business. One really important piece of the profit function that we're going to be looking for is what's called the break-even point. So profit can be negative. If your costs are bigger than your revenue, you have negative profit. You have spent more money than you have taken in. The break-even point is when we finally get to the point where we're not losing money. Okay, so this happens when the profit equals 0. It's called the break-even point. So we know that if we make one more than whatever that quantity is, we have now started making a profit. If profit equals 0, that tells me that revenue would have to equal cost, right? In order for this to be 0, these two things have to be the same. So depending on what you know about the problem, you'll either want to set profit equal to 0 or revenue equal to cost, depending on what you have. They're going to give you the same answer. I also want to point out here that this Q is consistent in this formula. So the profit at quantity equals 100 means how much revenue do I get from selling 100 of these minus the cost of making 100 of these, right? So the Q has to be consistent across the formula. So let's look at one example of this to make sure we can set this up. So let's go back to our ceramic pineapples. We know that our cost was 6Q plus 20,000 from before, and our revenue was 20Q. We were selling them for $20 each. What that tells me is that my profit function is revenue, 20Q, minus cost. And this is critically important. When you subtract off cost, you need to subtract off the entire cost function, which means you need to use parentheses because that minus has to go to both terms. The number one mistake that students make when working in business examples is not using parentheses and not having that negative go to the second term. That just happens all the time. So typically when we're dealing in profit, we want to combine any like terms. So here I have 20Q minus 6Q, which is 14Q. And then minus, because again, the minus goes to both terms, 20,000. Okay, so I'm going to graph this function so we can talk about what parameters we have on profit. Remember, revenue is positive, cost is positive, and they are both increasing. However, profit, we have our intercept at negative 20,000, and we'll talk about the rest of this in a second. Profit can be negative. If your cost is bigger than your revenue, you have a negative profit. You have spent more money than you take in. Is that good? No, right? We don't want to be in the hole money, but can it happen? Yeah, it can. So profit can be negative or positive. The point that we're interested in is this break-even point, the point where we change from losing money to making money. So how do we get this break-even point? Well, that's what we were talking about up here. We either set profit equal to 0 or revenue equal to cost. Since we have the profit function, we will set that equal to 0. We can bring the 20,000 over, divide both sides by 14. And we get Q equals 1428.57. Okay, that's a decimal right there. That's a quantity. So that tells me that's exactly where I make 0 profit. So if I want to make positive profit, that will start at 1429. I round up. And if it's a whole number, then I add 1. That's when I get positive profit. And this is exactly where I break even. Okay, so you'll be looking for break even points using our cost and revenue functions. Again, to take that next step from break even to positive profit, you either need to round up to the nearest integer, or if your quantity was an integer, add 1 to get into that positive range. So we don't have enough time for supply and demand, but I'll send you a quick video on that just so you understand what it is. Otherwise, I will see you guys on Thursday. Have a great rest of your day. Stay healthy, stay safe. Send me an email if you need anything.
You should ask people in the front if it's too loud, because like in the back it's fine, but I feel like they'd still be loud.
Yeah, it was a little bit loud in front, but I also felt like it was more important for people in the back here. I don't know. Maybe it was
I don't.
privacy.
Hi, I have a question. Is our professor gonna always be virtual, or will she eventually come to class?
She'll be, yeah.
Oh, for the rest of the semester, so would it just be like better off just learning from our dorm room, or